So this is in-class question number 1. Okay. We've got a mass of 1,500 kilograms. Okay, we've got a C of 1.5 meters. We've got a wheelbase of 2.6 meters. And so from those two values, we can work out what D is. It's 1.4 meters. Okay. The height is 0.6 meters. And we've got an angle, theta, of 5 degrees. Okay. And so we have our equation NF was mg d cosine of theta minus mgh sine of theta divided by the wheelbase L. Okay. And so we've got an mg in both of them, so I'm going to take them outside. 1500 9.81 divided by 2.6, and then inside the brackets here I'm going to put d 1.4 times by cosine of 5 degrees minus h, which is 0.6, times by sine of 5 degrees. Okay. And if you do that sum on your calculator, you should get 7,597 newtons. For the rear, there's a couple of methods. One is to simply employ this equation. So you can go through the process again. 1500 9.81 divided by 2.6. And you have C, which is 1.6 cosine of 5 degrees plus 0.6 sine of 5 degrees. (7062 newtons being the value for the rear normal load. Okay. The other way to work out the rear normal load is to take the total load and subtract the front one. So NR mg cosine of theta, which is our total load, minus the front load. And so if you do that, so in class question 2, so it's as above with the acceleration x double dot equaling 4 meters per second. Okay, and so we've got NF mgd cosine theta D is 1.2. divided by 2.6. And if you do that sum, $6,213, so you see it's gone down from before. And NR has gone up correspondingly. If you do that sum, that comes out to be 8,000. So in class question 3, for this one we've been given the mass at the front, 850 kilograms, the mass of the rear, okay, the height of the centre of gravity is 0.54 meters, the wheelbase is 2.8 meters, and the acceleration is 5 meters per second squared. And so NF, we've got the weight on the front minus mx double dot times by the height over the wheelbase, and so that's going to be mfg minus mx double dot h over L, which is 850, 9.81 minus 1800, because mf plus mr equals m. (5 meters per second squared). 0.54 is the height divided by the wheelbase, 2.8. (6,603 newtons). For the rear load, NR, is the weight on the rear plus mx double dot h over L. So that's 950, 9.81 plus 1800, 0.54 divided by 2.8. And that comes out to be 11,055 newtons. So that's the answer to part A in a sense, okay? To work out the one with the incline, we need to work out what the angle is of the incline. Well, if you 1 in 12 is basically 1 metre up for 12 metres long. Okay, so the angle theta is going to be the inverse tangent of 1 divided by 12, which is 4.76 degrees. So NF we need to work out C and D. So let's do that. We know what MF is. That's 850 kilograms, and we know that is D upon L times by the full mass. Okay, so D equals MF L divided by M. Which is 850 divided by 1800 times by 2.8. So that comes out to be 1.322 meters. Okay. MR, the same way. MR is 950, which is Cm upon L. So C equals MR L divided by M. 950 divided by 1800 times by 2.8. Clearly the alternative way of working out what C is to take the wheelbase and subtract D from it. It's the same thing. Okay. So just to add it together. Okay, so they're the wheelbase lengths. And so now we've got this equation, okay, but we've got the incline term in here. So the we've got the theta is now not 0, so we need to include both of those terms as well as these terms. So we can't use just that equation. That's just for low speed only. Which is the acceleration from sunset. Okay. So we've got to revert back to those equations that we had up there, NF and NR. So NF, we've got MGC. Is that right? Yeah, I've got them. I've just got these modeled up, haven't I? MG cosine of theta minus MGH sine of theta minus M x double dot H divided by L Oops.
funding for it.
Oh, good. That's all good.
I need a geared car.
Lads, they are still contract.
Education.
Come on. That might
Maybe a
still
single
more.
seater.
I'd buy your pie as well.
Tires.
Formula One, like our research. That's it.
There's a bag there if you want to go.
Where's the
Where's
ship?
Oh, that's not possible.
Everyone's trying to wait now. Everyone's trying to marry.
Even if it comes down to like
Have you seen that?
Okay, so once you do the
No, not yet.
once you apply this equation for the case when there is an incline, so this is also when this is 0. So it's this equation we've got to use. Okay. You get 6291 as your load. Okay, so it's gone down from 6603. But the incline is now 6291 with the same acceleration. And again, for NR, I'm going to use the quick method, which is just to subtract it from there's mg minus nf. So subtract it from the total normal load. So we've got 1,800, 9.81 cosine 4.76. So that's the total normal load, and we subtract 6291 from it, and we get 11,306 newtons. Second class question 4, part A, okay. Basically, we want to work out the tractive force, which is the aerodynamic force, plus the resistive force due to the roller resistance, FRL, okay. We've got the equations up there on the board. 1/2 rho CD AV squared plus CRL times by n, or R times by n. Okay. We've been given the various values. We need to work out the velocity though. That's 70 miles per hour. We know that in 1 hour you have 3,600 seconds, and we know in 1 mile we've got 1,609.344 meters in 1 mile. So the miles cancel and the hours cancel, we end up with meters per second. So this comes out to be 31.2928 meters per second, which is what we need to get force in newtons. And so, let's plug the various numbers in. Ft is 1/2. Rho, we've been told, is 1.225 kilograms per meter cubed. We've got a coefficient of drag of 0.3. We've got a frontal area of 2.16. And we've got velocity of 31.2928 squared, plus the coefficient of roller resistance of 0.01. And N is mg, so because it's level ground. Okay. And do those sums, you get 535.8 newtons. There's your tractive force on level ground to maintain 70 miles per hour. So for part B, we've got to find the power when the vehicle is travelling at 150 miles per hour. And we know that power is going to be the tractive force times by the velocity, which we'll call Vx. Now the velocity, 150 miles an hour, let's make that conversion to put it in meters per second. Miles per hour We multiply that by 1609.344 meters in a mile, and we've got 3,600 seconds in 1 hour. And if you do that sum, that comes out to be 61.056 meters per second. Now the tractive force required is going to be equal to the resistive forces that are being applied. So we've got the aerodynamic force and we've got the force due to rolling resistance, FRR or FRL, and that's times by x double dot, which is our velocity. And so if we do this sum, we get 1/2 rho CD A V squared plus CRR times by the normal force, okay? And that's multiplied by our x double dot term. So we've got 1/2 rho, which is 1.225, CD was 0.3, A was 2.16 meters squared, and then V squared, so we have 61.056 squared plus 0.01, which is our coefficient of rolling resistance, and the normal force, which is mg, so 1500 times by 9.81. Okay, and that is multiplied then by 61.056. So the tractive force itself comes out to be 1,931.8 newtons times by 61.056. And so the power required comes out to be 117.95 times 10 to the 3 watts, which equals 117.95 kilowatts. Now to get the engine torque, we can use this in the equation Ft equals the torque from the engine times by the gearbox ratio times by the efficiency divided by the wheel radius. And if we rearrange this equation for Te, we get Ft times by the wheel radius divided by the gearbox ratio times by the efficiency. If we plug in the numbers, so 1931.8 times by 0.31745 divided by 3 and divided by 0.9. Doing that sum, you get 227.13 Newton meters.